Welcome to episode 3 of Academic Paper Cuts. This episode, we interviewed Jacob Schulman, who is a PhD candidate at U of T studying medical biophysics.
He wrote a paper called Non-invasive perfusion MR imaging of the human brain via breath holding, which is a mouthful. But in general, it's looking at blood flow in people's brains using MRIs.
Yeah, so this was a very enlightening conversation for both Aaron and I. Jacob is very intelligent when it comes to the field of medical biophysics and other fields as well. It was very incredible. It was an incredible conversation, and we hope you guys enjoy listening to it.
Enjoy it.
Welcome to Academic Paper Cuts, episode 3. Today we have with us Jacob Schulman. Jacob, thank you for coming.
Of course, it's a pleasure to be here.
So Jacob is a PhD from studying medical biophysics at the University of Toronto. He did his honors. Bachelor of Science in neuroscience, biology, and chemistry at U of T as well. And today he's here with us to talk about his academic paper titled. Aaron, what's the title? It's a bit of a tongue twister.
We got non-invasive perfusion MR imaging of the human brain via breath holding. That's it. You got
that spot on?
Word for word.
All right.
Like an iceberg.
So the first thing we like to ask our guests on the podcast, Jacob, is let's say you're talking to your cousin at a family dinner who's in grade 10 or grade 11 and they ask you what your paper's about. How would you describe that to them?
So it's a good question. So in general, the goal of this work is to image, like imagine taking a picture, literally with a camera. We're trying to image in 3 dimensions blood flow in the brain without doing anything invasive. What I mean by invasive is like putting a needle on somebody's arm and injecting something. We're trying to do this in the absence of anything that would be considered cutting into somebody or essentially that.
And is that how they currently image the brain?
Currently, to image the brain for perfusion, which is a specific type of imaging.
Okay, we'll get into that in just a second.
I'll definitely touch on that. It's required to provide a contrast agent. And a contrast agent needs to be injected, which is invasive.
And a contrast agent just does what? It allows you to see the brain against something, so it's easier to identify what is the brain versus something else?
So the contrast agent is something, for the purposes of this type of imaging, it's a substance that is going to go into the bloodstream. And essentially what it's going to do is amplify the signal that the scanner is going to detect, specifically in parts of the brain that contain blood vessels.
Aha, because it's only in the blood, and that's the only part. Okay.
Hopefully.
Is that used on other parts of the body?
Yeah, it could also get out of the blood, but that's a whole other story.
Okay.
And it is used on other parts of the body. Yeah.
But it's only useful where blood flows.
Exactly. If there are no blood vessels to, like the fingernails, for example, then you're not going to be able to pick up sort of a signal change from the contrast agent.
Very nice. Okay. So the second question Aaron and I usually like to ask our guests is to just go word by word through the title, just so we know high level what this paper is sort of going through.
Sure. Yeah. So we got, I think the first thing would be, I think you kind of touched on it, like non-invasive.
Right.
You're saying like we're not going into the body at all, like we're not injecting anything, and that's what you're saying. Like in this case, is that exactly what it is? We're not.
That's pretty much it. We're trying to avoid getting into the person, essentially. Okay. Putting anything into the person, whether it's a needle or a tube or anything like that, we're trying to avoid that. That's non-invasive.
Okay, awesome. And like in this case, you're saying like you're injecting. We read it was like gadolinium. Is that what exactly it is? Typically is injected.
Exactly. That's the typical agent that's
used. It's like a metal, right?
It's a metal, cool. Exactly, and that needs to be administered through the vein, typically, invasively.
Yeah. Totally makes sense. Yes. And then we have here perfusion.
Right.
Like what is that? Like is that sweating? Like what
right.
is that?
So it sounds like it's a bit like perspiration. But perfusion is blood flow basically.
Okay.
It's just another like a fancy word, a fancy way of saying blood flow.
Oh, okay.
Basically how fast the blood is traveling in addition to how much blood is actually traveling.
Okay.
Yeah.
So we'll get into why that is important too. Let's finish off the title.
Yeah. Sure. And then MR imaging, does that mean MRI basically?
Exactly. MRI is magnetic resonance imaging, and it's a specific type of imaging technology that exists.
Okay,
We can talk more about that if you want later.
for sure. We'll definitely want to talk more about that.
Yeah.
And then we have human brain. I think we kind of know what that is.
Yeah.
And then
we all got one.
this was only me and David were like, was like breath holding. Like,
Is it literally holding your breath? There's nothing more complicated to it. Just holding your breath. Okay, good. We were talking about that for a while. But are we doing this right or not? Okay, great. So I think where we should start now is, so the problem of this invasive, the status quo right now is the invasive aspect of this, which is was it gadolinium? Gadolinium.
Okay.
Yeah.
So is there like side effects of injecting this metal into your body? Like, why are we trying to eliminate that? Obviously, it's inconvenient, but
there's a few reasons. There can be side effects. There can be. I think in 4% of people who use it, there are. But there are actually groups of people who literally cannot use it, meaning that there are those with kidney disease, for example, who can't filter it out properly.
And it remains in their blood.
It just remains in the blood, and I think in like 21% of people who have kidney disease, they'll actually develop a disease and die.
If they use
gadolinium, which means that they effectively try to avoid injecting gadolinium in these individuals. That's one motivation for trying to avoid its usage. One other would be the price. It costs a decent amount of money. I actually don't know the exact price, but it's relatively pricey for the injection itself, even for a very, very small.
Is it because the material, the metal is expensive?
Heavy earth metal.
Yeah. Anything in medicine is going to cost. I think in medicine they're going to bump it up a little more than maybe what it should be worth, because it's necessary, right? It's critical. At least up until maybe recently, it was very critical. And so it's a metal. It's relatively rare, I believe. So that could be part of the reason. But again, just in general, in the biomedical world, things are expensive.
And is this the only way right now that people can image the brain the way you're talking about it?
No. It's a very good question. It is one of, I would say, 3 ways that you can image the brain, image perfusion in the brain. But this sort of subtype, I would say, this subtype within perfusion imaging is the most, I'd say, simple. It's the most easy to use across different scanners. So if you go to the hospital in South Korea and you go to a hospital in Toronto, it'll be very easy to sort of collect this data. Whereas if you were to use one of these other modalities that are relatively new, but I haven't discussed yet, it would be harder and therefore less clinically translatable, I would say.
And this is you're talking about the gadolinium?
Yeah.
Okay.
Gadolinium versus...
So this is like the industry almost standard, is what you would call it.
This is the industry standard.
Yeah. Okay.
Exactly. The clinical standard.
And you were saying with it before, like, it's meant to amplify the signal. And in this case, does that mean like the actual like magnetic field strength because it's MRIs or?
Yeah. So it's actually complicated when I think about it. It's actually not that we're amplifying the signal, it's that we're decreasing the signal, believe it or not, in these regions. And this becomes very complicated. We can like take it step by step. I don't know if you want to do that.
Yeah. Well, let's jump into it. Yeah.
Sure. We'll try. It's very complicated. So in MRI, essentially what's being done is you put a subject in the scanner and there's a very, very powerful magnetic field. I don't know if you've heard of like the term 3 Tesla magnet or 7 Tesla magnet. That basically describes how strong the magnetic field is. So you put somebody in there and effectively every hydrogen proton within their body is going to experience that field. And the hydrogen protons actually have a magnetic spin. And so they're going to be aligned with the magnetic field in the direction that it's being applied.
Yeah.
So all of a sudden they're in the MRI, all their hydrogen protons are pointing in one direction, right? And what's going to end up happening is you're going to sort of apply a pulse, a radio frequency pulse, we call it, an RF pulse, and it's going to disturb the protons, basically. It's going to offset them from their
aligned with
the field, exactly. And they're now going to tip, depending on how long you apply that pulse, they're going to tip into what we call the transverse plane, which is sort of like perpendicular, 90 degrees.
Yeah, okay.
When that happens, they'll typically sort of relax back into their original field, into the original direction of their alignment. However, as that occurs, there are other processes that will cause these protons, which are normally spinning together at the same frequency and sort of the same phase, to start to dephase from each other.
And nothing's aligned anymore.
Things start to disalign.
Okay.
Exactly. So they're sort of like now one's spinning at like some frequency X and the other one's spinning at some other frequency. And we would say, for all intents and purposes, if we don't add a contrast agent, this is not entirely true, but if we don't add a contrast agent, we can assume they're all kind of spinning at the same frequency. The moment we add a contrast agent, what ends up happening is the contrast agent disturbs the spins in such a way that if the protons are closer to the contrast, they're going to end up spinning much faster. And the protons that are further from the contrast are going to spin at whatever rate they were at before, probably a slower pace. And so what you end up getting now is some protons in the imaged part of the brain are spinning really quickly, some are spinning really slowly, and when you summate these signals together, it actually ends up subtracting from itself. Because you have some protons that are like, it's hard to do this, I guess, not visually, but if you imagine vectors are sort of like, can I use that term?
Yeah, that's good.
Arrows.
Okay, arrows.
Yeah, with a link.
Exactly. If you think of like arrows that were sort of stacking one on top of one another, if they were all sort of in the same direction, we get a nice long arrow, right? But if we have the same amount of arrows, now one's pointing this way, one's pointing to the left, one's pointing to the right, and we add those all up, you get a much shorter arrow.
Yeah.
And so what ends up happening is in parts of the brain where we have a lot of blood vessels, and therefore a lot of contrast, because the contrast is limited to the vessels, those parts of those regions of tissue are going to end up having these smaller arrows in comparison to regions of the brain that don't have contrast.
And we want the smaller arrows, is that?
So it's not necessarily that we want the smaller arrows, it's that by comparing the big arrow, which is what it originally would have been, to the smaller arrow, which is what it is now at the contrast, you can actually, depending on the difference, get an idea of the amount of blood. The amount of blood volume.
In different areas.
Like you know what it should be. If there's no contrast.
Right.
Now we're adding the metal, which is going to disturb the magnetic field by accelerating some of the spins.
Right.
And then we'll get a smaller arrow because of because there's a difference in the spins of the protons.
Right. So you can almost imagine like a before and after photo. Right?
Yeah.
Before that's, I guess,
before we have they're all spinning at the same rate. After we have different,
part, yeah.
And that different causes it to be smaller. The
contrast.
The contrast.
Right. And then different parts of the brain have, of course, different amounts of blood vessels and blood vessel density. And so effectively, by comparing the before and after, you can determine which parts of the brain have more blood and which parts of the brain have less blood. And there are parts of the brain that have more and less blood. It's not uniform. That's the nice thing about perfusion.
Is it purely a relative measure, or is there like, do you guys use like a reference number? Like we know that when we have gadolinium in this area, we know the actual vector length, and then we compare the relative? Or is it just relatively there's more here than here?
It's a really good question. It becomes quite complicated, and I would say that for the most part, clinicians are interested in about how does it compare before and after.
Okay.
That's really the main concern. When we want to get really quantitative and say, okay, there's exactly 4 milliliters of blood in this part of the brain, and there's exactly 2 milliliters, which, by the way, nobody has been able to do just yet. This has not been done in the field. But when people try to do that, they have to bring in all these corrective measures and all these algorithms, and it becomes very messy and not very translatable from one sort of means to the other. Generally speaking, you've got it. It's mostly how does that long arrow compare to the short arrow, and we do that in every single pixel of the brain, and you get your sort of perfusion map.
So I don't understand why we couldn't just use, like, why we need the contrast agent. Is it because if they're all spinning at the same, you said the contrast rate is going to disturb the spins, right? So what makes them all spinning at the same rate hard to measure?
So let's say we didn't add a contrast.
Yeah.
That's sort of what you want to explore, right? If we didn't add a contrast agent, we got our before and after picture. The before picture, so these spins are all aligned. We disturb them with the pulse. They're all spinning. And generally speaking, I'm going to say they're going to spin at the same rate. And so they're not going to get offset from each other. And so you get that nice big long arrow. But if you do an after photo and you do the same thing that you did before, then you get the same area you had before. And therefore, when you subtract the before and after, you get 0. There's no change.
So what you're doing is you measure the brain before, you measure the brain after, and from that difference, you could apply a pixel and you could get a picture from that. Yeah.
So interestingly, we're actually not necessarily doing a before and after. We're acquiring information at like every second or every 2 seconds. So when I say before and after, I'm simplifying. You can imagine like at time point 1, we've got some signal. At time point like 10 seconds, it's got the minimum signal. And at time point 20, it's gone back to normal when the gadolinium passes out of the brain.
Yeah.
But of course, we're sampling this. I guess you could say like the sample rate is once per second or once per 2 seconds. So we're actually acquiring quite a bit of data as this gadolinium is passing through the brain.
And it's like a specific, like, you could think of it maybe as like a tube passing through, kind of.
You can think of it as like, we like to call it a bolus, but yeah.
What is that?
I don't even know. So I think there's an idea in like digestion where you eat food and it goes down as like a bolus of food.
Okay, so like a group.
Yeah, it's almost like this like bump, this time course where you have like over time you get this sort of change in signal. I think like the y-axis is signal and the x-axis is time. You get this like bump decrease in signal over time, which should reflect the amount of contrast agent over time. When you see like a much larger change in signal, that means there's more contrast in the brain. When you see it's going back up, it means there's very little contrast now that's getting out of the brain.
And
it's the idea.
I'm just curious of how we get the picture from the contrast.
How do we get the picture from the contrast?
Like, why do we need the contrast for the picture?
Right. So theoretically, you can take a picture without the contrast, and you got a picture of the brain. In fact, there are many types of MR methods where you just get what we call an anatomical image. And those are beautiful images. You get like a really nice pixel-wise image of the brain. You see everything very clearly. It's great. But that's not perfusion. That's more anatomical. It sort of shows you the general structure of the brain.
Because we're measuring blood over time, right? So we can't just take a snapshot. We need all of it.
Right. So it's two things, I think. It's one thing is that when we take an anatomical image, we're not exploiting any blood properties. We're just getting like an image of the brain. And there are other reasons why we can get that information. When we do perfusion imaging, we're specifically trying to exploit something in the blood. What specifically like in the blood that's not outside the blood is going to allow us to get a little change in signal. That's effectively what we're trying to do with perfusion imaging.
Gotcha.
So you're right. You can get a picture of the brain without contrast 100%. Those images aren't called perfusion images. They're called anatomical images, diffusion images. There are all these different types. But perfusion is a very specific type, which is, for whatever reason, one of the most clinically relevant images you can get. And that specifically targets the blood vessels and the blood flow in the brain.
Okay.
If I were to like boil it down to the main reason, would it be like every blood cell looks the exact same if you don't change anything to it? So if you take a picture now and a picture after, it looks like it's the same blood cell passing through. So we kind of need to change it with the metal so that we can actually distinctly point that one out and see what's happening as it moves, because you care about the movement, because you care about the blood flow.
You pretty much have it. It's like not even necessarily the blood cell, but like just if you take a unit of blood, which means like let's say hundreds of blood cells, a bit of plasma, all these other components, you take that unit of blood and you look at it over time. If you don't do anything to it, it's the same blood that it was here as it is going to be 2 months later.
So this creates a distinction.
It creates a distinction. Now the question is why we need the distinction. The reason is that you can't pick, it's very hard, almost impossible to pick up on the blood vessels without creating that distinction. Because you need some sort of magnetic change to arise from those vessels to then change the signal specific to where those blood vessels are. If you don't have that, then it's just, you get a picture of the brain, but not anything related to the vessels, just related to other things.
That makes sense. There's an analogy that comes to mind of like zebras. If you look at like a pack of zebras, they'll stripes, they all look the same. If you like paint one of the zebras with a color, you can pick it out and then the lines can like hunt it down.
Yeah, so that's like the contrast.
So
the painted zebra is like the contrast if you don't know it in your analogy. Yeah, and then you can pick it up and you can see it all of a sudden.
And you said that perfusion is very clinically relevant. What's it used for? Like for diagnosing brain issues, blood flow issues, brain issues.
Yeah. So this was, for me, it was an interesting experience because about 3 weeks ago, I shadowed a radiologist.
Okay.
I have to like see what they're doing, how useful is my work, how useful is like we do in the research. A lot of the time, you're thinking, okay, I'm making this really small change, this really small contribution, and that does happen to be the case a lot of the time. But when you go in there and you see what the radiologists are doing, you actually see them sort of applying the methods that either you've been working on or your colleagues have been working on. It gives you a really good sense of how far the research is being implemented into the clinic. So one thing that's done is perfusion imaging allows clinicians to differentiate between the aggressiveness of cancer in the brain. That's a fairly common one, and I think the first paper on this maybe came out in the early 2000s.
It's like the more the blood flow, the more aggressive.
Yeah, there's a very special thing that cancer does in the brain and also in other parts of the body, known as angiogenesis, which means it recruits its own blood supply. So
what does recruits its own blood supply meaning?
What that basically means is if you got like a little region of the brain where the tumor cells start dividing really quickly, in the early stages, they're just using the blood supply that's in that region. It's not necessarily doing anything. That's sort of true, sort of not true. As the tumor gets more and more aggressive, like it starts dividing more rapidly, it gets more mutated, it tends to, not always the case, but it tends to develop this ability to stimulate the blood vessels to actually grow out towards the tumor and supply the tumor with its own unique blood supply. Yeah.
Wow.
So basically, if you look at an image, going back to perfusion imaging, if you look at an image of a tumor patient, you may not see anything if it's a really early stage tumor. You'll just see, okay, the blood supply in the X area of the brain and Y area of the brain looking totally normal. And the area where the tumor is, you don't necessarily see anything abnormal just yet. But come back 4 years later, or probably a little bit sooner, maybe 2 years later, the tumor's gone really, really aggressive. All of a sudden they take a picture again and it's lighting up deep red. Like there's a ton of vascular supply there now. Now the blood volume and the blood flow is very, very high on the
and that's because it's basically creating like its own highway to the tumor.
Exactly.
Okay. So it's very useful in tracking the severity of cancer in the brain.
Right. So there are definitely other things that can be done with it. One is stroke imaging. I should also mention that in perfusion imaging, there are different measures you can get. There's blood volume, there's blood flow.
Yeah, this is something we always ask people, like, what do your results look like as like a unit? Like, what are you looking for? Is it like, if it was an Excel table, what are you looking at?
What are your columns? Like, what are each of those?
Right. So we're often interested in a few different measures. One is blood volume, one is blood flow, one is what we call the mean transit time. They're all very related to each other. They're definitely unique, but they're very related. Blood volume is just how much blood there is in some pixel of the brain, or we like to call it a voxel, which is like a volume pixel of the brain. So that's a simple one. That's just at any given moment in this area of the brain, how much blood is there. Mm-hmm. Blood flow is how much blood is moving through per unit of time. That's blood flow. And then mean transit time is basically the average amount of time it takes for blood to pass through that region. There's actually an equation that just relates these three things to one another. They're very much related. But each of them actually have slightly unique uses in the clinic. So what I just told you about the cancer, that tends to be something that clinicians will use blood volume and blood flow measures for. Not as much the mean transit time measure. However, the moment that you start getting interested in things like stroke, that's when clinicians might start to say, oh, we're interested in this mean transit time measure instead.
Okay.
This one will give us more information.
So different properties for different issues.
Why is the mean transit time important there, though?
Good question. So when the tumors recruit their own blood supply, I don't want to say this as a super general statement, but in general, the amount of time that it takes for blood to pass through is going to remain relatively the same.
The traffic's the same.
The traffic is relatively the same. The amount of blood is clearly substantially different, but the time that it takes is not going to change too much, or it shouldn't, ideally. That's not always the case. But when we move to stroke is a disease where we know that the blood supply has been like totally cut off or heavily reduced. And so in those regions of the brain, we're not only going to see, say, a reduction of blood volume, because the blood's been totally cut off, but we're also going to see it's going to take a lot longer for blood to pass through there. So those regions.
There's less blood, and a given, like you said, piece of blood is taking longer to go from point A to point B.
Exactly. So it's like all three things are now coming together.
Does that have to do with like pressure of like the blood vessels? The more blood you have, like.
Yeah, for sure. So there are different types of strokes, I guess, that you can have. One would be like a hemorrhagic stroke, where you have the blood vessel like rupturing. One is just where you have the blood vessel that's being blocked. And I think that specifically for the case where we have the blood vessel being blocked or occluded to any extent, that's going to narrow the blood vessel, of course, and it's going to take more time for blood to pass through. Mm-hmm. So the amount of time it's going to take for stuff to pass through naturally take more time.
So it's not really like throughout this whole distance, if we take some length, it's not that it's going slower through the whole length. It's more like it's going fast, slows down, and then speeds up, kind of like that blockage.
Yeah, and that happens even in healthy people. And in all of us, that's happening. Meaning, like, the blood is flowing super quickly in our carotid arteries in our neck, right? But then we get to the brain, and these vessels get smaller and smaller and smaller, and the velocity of blood becomes super, super slow, which is really important because if we want, like, oxygen and carbon dioxide to transfer between the tissue and the blood, we need things to be moving a little more slowly. If it was moving too rapidly, it might be a little bit harder to transfer, right?
Because we need the let's call it nutrients in the blood to be absorbed by the brain, and that's why it slows down.
Right.
Whereas in the neck, not as much needs to be absorbed.
Right, exactly. In fact, in the arteries, typically things don't get transferred. In the veins, typically things don't get transferred. But at the capillaries, which is like the really, really small vessels where blood flow is super slow, that's where we want things to be really slow, so that things can transfer.
If it's going faster in our neck and slow in our brains, but overall the blood circulation in our body is relatively, like, it's not slowing down, it's constant. Does that mean that I know it's slowing down at points, but if you look at the system as a whole, right, if you're just sitting down and not changing your heart rate, your blood's flowing at the same rate. Does that mean that there's just more, like, if you think there's more smaller tubes in the brain, whereas one bigger one in the neck? Is that how they could slow down?
You're asking a really good question. In the question, I'll try my best to explain it. The blood flow in the large artery, as it turns out, the overall volume, if we added up all the capillaries in the brain, that volume is way more than the arteries that are supplying the brain. I'll try to restate that. Yeah, I know. So, like, you've got, like, a little bit of volume going into the brain. You've got, like, 3 arteries, let's say, 3 major ones. You've got, I don't know, millions of capillaries. So if you add that all up, it's actually a really, really big volume.
So it's like there's some extra blood staying here.
So you can almost imagine it naturally has to slow down in these regions because there's so much more volume, right?
Yeah. So
the blood's, like, flowing out super quickly, but it's, like, spitting out blood into all these different vascular paths. Mm-hmm. And so it needs to slow down and then sort of speed up again. This is actually a basic, like, physics fluid dynamics principle, basically. You may or may not be familiar, but it's something that took me a really long time to understand. And then somebody said to me once, this was like first year physics. And I was like, oh. I was like in my third year of my PhD. Like, what is going on? Why is it slowing down? Why is it speeding up? But no, apparently it makes sense and it sort of works with physics. And so long as the flow overall is kind of conserved, then that's what matters. And theoretically it is.
The thing that keeps coming in my head is like electrical engineering with circuits.
It's exactly
it's like Kirchhoff's law, where it's like the current splits, so the current going into a node, it has to slow down if it comes out 2 ends. So the current has to be smaller.
It's like 100 parallel circuits. They're exactly from capillaries and they come back at the end.
Yeah, same.
Aha, okay, that's a great analogy. Okay.
Yeah, for electrical engineers, that would be
only for electrical engineering.
By the way, I use electrical, like, engineering ideas for a lot of simulations because they're very interrelatable, like interchangeable.
Like the math, essentially.
The math, it's quite interchangeable, at least from, like, a very basic theoretical level. It's very interchangeable. Yeah.
That's really, really interesting. Mm-hmm. That's awesome. Mm-hmm. The thing I'm curious now is, like, we're talking a lot about, like, how all that works. So what have you changed about that with this breath holding? Like, what's making that different now?
Yeah. We haven't even got to the breath holding. Actually, that's it for the vapor. We've been talking about what you've been trying to fix the whole time.
Right. That's the big one. So I guess I'll start off before the breath hold, describing something that came out just slightly before. This was our first project, and I didn't want to burden you guys with the first one because that was messy and it's, like, super, super long, and I think this one's more interesting. But our first paper sort of created the framework for what we did here. The first one, we explored the possibility of creating what we call endogenous contrast. Endogenous just means it's already inside of us.
Okay.
We don't have to, it's non-invasive essentially, but the way that we get it to be non-invasive is different than the way we did it here. And so with the first paper, we were interested in modifying the amount of deoxygenated hemoglobin in the blood.
Which means?
Yeah. Right. There we go. Here we go. So hemoglobin, which is
carries the oxygen in the blood, right? I remember grade 9 science.
Beautiful. Carries the oxygen in the blood. As it turns out, when it's not bound to oxygen, it has a very different magnetic property than when it is bound to oxygen.
So the chemical composition completely changes its electromagnetic properties.
So you can almost imagine like the structure itself stays kind of similar, but when you take off that oxygen, the amount of electrons, unpaired electrons, increases, and that makes it more magnetic.
So the field is completely changing, essentially.
If you put it in a magnet, it's going to change the field. In fact, the idea is that if you compare it to gadolinium, the deoxyhemoglobin kind of does the same thing. That's the point.
And so this is just blood in our body where the hemoglobin doesn't have deoxygenated. Okay. Now that the hemoglobin doesn't have oxygen, it changes the electromagnetic properties.
Right.
How does it lose oxygen?
That's a question.
Okay.
Right. So one way you can imagine is breath holding, which I'll talk about soon. The other way was in the first project we used a gas control system. And the gas control system was like you had somebody masked up to a machine, and that machine you can actually target. You can target the exact amount of oxygenation in the blood that you wanted.
Because it's very precise,
it's very
right?
Precise.
It's measured and calculated, whereas holding your breath is less, I'd imagine.
Yeah, exactly.
It's person to person.
It's person to person. And also, like, at that time, people didn't think it would be possible to do this with breath holds. They were like, there's too many things, which we'll get to. But with the machine, it was very precise, like you're saying. You can control it to exactly what you wanted as long as you didn't kill the person. Because if you lower it too much, it's
like push the limits of the experiment a little bit.
Right. So typically we were using like milder hypoxia, so you wouldn't even feel it. Even for like the more moderate ones, I wasn't feeling it when I went in the scanner. And the idea here is you're lowering the amount of oxygen that's inhaled, right? And so all of a sudden, the hemoglobin in your blood just typically bound to oxygen. In the arteries, like 98% of it is bound to oxygen, or 99%. All of a sudden, those arteries are now getting way less oxygen than they expect to get in the lungs. And now they're dropping down to a saturation of like 88%.
Okay.
So what does that do? Essentially, if you imagine over time, we can change the amount of oxygen, like a bolus, like I described before with gadolinium.
Yeah.
You can effectively do the same thing, get the same effect overall with signal change. Because again, if we think of deoxyhemoglobin as very similar to gadolinium in terms of its magnetic properties, it is a little different, but in general, we'll say it's the same. Then by injecting gadolinium in the blood and having it sort of increase over time as a bolus, and by modifying the gas sort of oxygenation levels.
Okay, I see.
And changing effectively the amount of deoxyhemoglobin, you get the same effect.
So, do you have to adjust anything from the MRI standpoint, from the imaging standpoint, to calculate? Because you said they're generally the same, but the properties must not be exactly the same.
Right.
They do in the electrical field.
Gadolinium is still considered a much stronger magnetic moiety. Like it's much more powerful. For every unit of gadolinium, you're going to get a bigger change in the magnetic field, which is good for contrast to noise and for these sorts of things and for signal change. But deoxyhemoglobin is non-invasive. So it's a big trade-off. You're getting sort of this non-invasive aspect. Yes, it's not quite as powerful, but it's not invasive.
So the results aren't is accurate the right word? As detailed, maybe?
As detailed, I think, is more better. Like the resolution, maybe, of the results, you'd have to sort of slightly lower the resolution for the scans. Mm-hmm. But I will say that for our first project, we didn't change anything. We didn't change the resolution. We didn't change any of these properties. Sort of left it exactly the same. We said, let's compare gadolinium to this deoxyhemoglobin method and see how they compare to each other. And we sort of had to optimize the protocol a little bit, but we got results that were not too far off from gadolinium.
And are they useful enough? So let's actually just clarify. So we are taking oxygen out of our blood by holding our breath. Right. And by doing that, we get the same electromagnetic properties, so we can measure that contrast in the brain.
Yeah, so this one with the breath holding is actually really complicated the way it works.
Okay, so
with the gas.
Right, with the gas.
The gas, you're just literally, it's much more simple, removing the oxygen from the blood.
Exactly. Gas control, it's you start off with some oxygen, or we'll keep it even more simple. You start off with some amount of deoxyhemoglobin, way more deoxyhemoglobin, and then back to normal, and that's going to create that signal change. Yeah. Done. Simple as
holding your breath is not as simple.
Holding your breath, unfortunately, is not as simple, and part of the reason, it's part of the reason that people didn't want to work with it, I think, for at least in this setting, in the case of perfusion imaging. With breath holding, it has a physiological consequence to hold your breath. And the main physiological consequence is when you're holding your breath for, let's say, 15 seconds, which is what we did roughly, I think 16 seconds, the amount of oxygen in the blood of the arteries in the lungs, or I should say the capillaries in the lungs, actually doesn't change very much, like at all.
If you just hold your breath for 15 seconds.
Yeah, it actually changes maybe by like 0.5%, probably even less. Whereas I said with the hypoxia, it changed like 10%.
Yeah, like 98 to 88.
Exactly. With a 0.25% change in oxygen, you pick up essentially nothing on MRI. Mm-hmm. So the question is, okay, then why would we do this? And something else that's really interesting happens, which is that we get this increase in CO2. And it's quite a substantial increase in CO2, which is carbon dioxide. Carbon dioxide is obviously not hemoglobin. It's not deoxyhemoglobin. It's not changing the magnetic properties. In fact, CO2 doesn't do really anything to the magnetic field at all. But it does something really, really interesting that has been exploited in other works for different purposes. CO2 has a very special ability to dilate the blood vessels. Okay. So what is that? How does that? Yeah. So what's going on? Okay. So you dilate the blood. I'll try to keep it like a simple model. Imagine you got a volume of blood or a volume of tissue, and there's a few blood vessels going through. All of a sudden, you get this bolus of CO2, this sort of time course of CO2 that passes through, and then it goes away. The more CO2 you have, the more dilation you're going to have. And the more dilation you have, the more blood flow you're going to have. Because if we think about the fact that blood vessels are quite resistive, like a resistor in a circuit, if we increase the diameter of the blood vessels, we reduce the resistance.
So you're like taking, just for those listening, it's like a hose that you expand the hole of the end of the hose so more water can come out.
Right, exactly.
And there's like the source is not infinite, but like the sources can push as much as possible. It's only the same amount's going to go through.
Yeah, like the source, like the heart. Yeah. Is effectively, we would assume the heart doesn't really change. So like the pressure difference, I want to say, doesn't really change from like here to here, like from into the brain to out of the brain. It doesn't really change. But what's going on inside of the brain is that each of those individual vessels, specifically the arteries and arterioles, which are like the blood supplying vessels, are going to dilate. Okay. Now blood flow is going to increase.
So more carbon dioxide, we're holding our breath, now our arteries are dilating now, so more blood's going through them.
Right. More blood's going through at a more rapid rate. Okay, great. What does that do? There's no change in the magnetic field, at least not up until this point. But it turns out there actually is, because what happens is that when we get to the tissue level, if you have an increase of flow, if more blood's going through at any given moment of time, we have to keep in mind that the tissue in the brain, like the neurons that are surrounding like the blood vessels, which are actually eating up the oxygen, they're only eating up the oxygen at some rate, right? Now the blood flow is increasing. That doesn't change the rate that the neurons are using that oxygen, right? They're still using.
Oh, so there is a change.
So there actually ends up being a change, because what happens is at any given moment in time, let's say the amount of oxygen in the vessels is like, 75% in the capillaries, let's say. I think it's roughly around there. If the blood flow is now increasing, then at any given moment of time, we're actually, or I shouldn't say any given moment of time, if you like average over a few seconds, the brain tissue is getting it's seeing more oxygen. And therefore, at any given moment of time, it's going to end up extracting less oxygen.
It's seeing more oxygen. So
like, let's say over 3 seconds. Over 3 seconds, let's say the blood flow is 3 milliliters per second. All right? Well, I'll try to do, I guess, like somewhat mathematically. Over 3 seconds or 2 seconds, let's say. 2 seconds, the blood is flowing at 2 mils per second. That means that tissue is seeing 4 mils over that period of time. Now, all of a sudden, we've increased the blood flow to like 8 mils a second.
So we're going to see 16 milliliters
16 mils over that time, which you can also think of as oxygen, 16 oxygens over that time.
Yeah.
But the brain's still only using like 2, right? That's not changing.
So, okay. And then, so that now we'll remain with 14, which is more than the 2 that was left over.
Yeah.
And that change, how does that affect the magnetic field?
Right. So remember, it's all about deoxyhemoglobin and hemoglobin. It's like a ratio between those two. We now have a much higher ratio of hemoglobin to deoxyhemoglobin, right? Because we've extracted less oxygen, like you just said. Yeah. We've only taken out 2 now.
Because the deoxygenated remains no matter what. It's only the oxygen that will get extracted.
Right. So exactly. So you've got the deoxygenated hemoglobin, you've got the oxygenated hemoglobin, and from that oxygenated hemoglobin, we're taking out X amount of oxygen. But if that blood flow is much more quick, we're taking out way less oxygen.
Gotcha.
Because you've got so much more than supplying per second.
Yeah.
Yeah, per unit.
But we're taking a smaller percentage of the total oxygen we're bringing. Okay. Now.
So now you've got
a different ratio.
And that's going to cause a signal change.
That actually changes like the magnetic properties of the blood.
Yeah, because what we're effectively doing is, relatively speaking, reducing the amount of deoxyhemoglobin.
So you're measuring the reduction of the oxygenated hemoglobin, not the increase. Before it was the increase.
Exactly. So with the gas control system, we wanted to do hypoxia. Hypoxia was reducing the amount of oxygen and therefore increasing the amount of deoxygenated hemoglobin. With the breath holding, we actually kind of do the opposite. Which is weird. You would never think
you flipping the script.
Breath holding, you're like, oh, I'm getting less oxygen. But remember I said oxygen doesn't really change in the lungs for 15 seconds.
So you're measuring how much less deoxygenated the amount of oxygen remaining is more, meaning the ratio of oxygenated to deoxygenated is higher, and you can measure that change in signal.
The ratio of oxygenated to deoxygenated is higher. That's literally it.
Okay.
Got it.
Okay.
What's a good analogy is to explain that to people?
Oh my God.
I'm kind of thinking of when I'm thinking of it, it's a pretty brutal example, where I'm thinking of like bags on a carousel at an airport. You know, like when you go to retrieve your baggage, you have white bags and you have black bags, right? Right? You want to measure if it's a 1-to-1 ratio, right? Then if you're trying to take off your bags or whatever, you're looking for just the white ones, then it's easier. But we're now increasing the amount of black bags, the amount of oxygenated hemoglobin. So there's a different ratio of white to black bags, right? But we're still only taking off a few black bags. I'm kind of butchering this, but
so it's my bag. Because there's one thing I maybe should have pointed out, which is that we're actually not taking out the hemoglobin. The hemoglobin's staying in the blood. Like the blood cells, they stay there, and the hemoglobin's attached to those blood cells, like effectively permanently. What we're taking out is the oxygen. And so by having that blood flow much more quickly, we're taking out less oxygen. And what that basically means is that you're now going to have, at any given moment, way more oxygenated hemoglobin in the blood. We're not necessarily taking out the oxygenated hemoglobin, we're just taking out the oxygen. And by taking out the oxygen, you turn that oxygenated hemoglobin into deoxygenated. But now that we're taking out less of that oxygen, you just have more of it in its like
ignore my analogy, listeners.
You almost imagine like painting the suitcase as like white or black.
Yeah, exactly.
Because you can turn one to the other. The black and white suitcase, you can turn a black one into a white one and a white one into a black one. All you have to do is add or remove the oxygen.
Okay.
Effectively.
So what we're doing is you're increasing the amount of blood vessels by dilating the arteries, right? Or not blood vessels, blood cells, blood flow.
And volume, but yeah.
Now there's more oxygenated. So now that there's more oxygen, when the brain absorbs that oxygen and turns it to deoxygenated, we could monitor that change, whereas before it would be relatively constant. Right.
So remember in the original example when we were talking really early on, I mentioned that you can take an image of the brain from time point A to B or 1 to 2 and not change anything, not add any contrast, and you just get a picture of the brain. It's an anatomical image, it's a whatever, but it's not a perfusion image. The way that we get perfusion images is by changing some magnetic property of the blood. You can do that with gadolinium, you can do that with hypoxia, you can do that with breath holding.
Very cool.
And theoretically, all three, they do it in a very different way, but all three are going to change the magnetic properties of the blood.
That's the only thing I'm struggling with is on the third one, the way I'm kind of thinking of it is like you have like, kind of like what Dave was saying, it's like you have a constant carousel of like deoxyhemoglobin like moving along. So I'm just a bit confused, like how is it that the actual magnetic property is changing? If it's like you always have like, let's say 4 deoxyhemoglobin per this unit space, or from that change in the blood flow, you're actually changing it to only having, let's say 2. Because I can understand that the concentration of it is changing. Like there's less per unit of volume. But I would think in my mind that the thing that's actually would change the magnetic property if the right oxygenated hemoglobin actually has no effect on the magnetic properties at all, then it would be the pure amount of the oxyhemoglobin.
It's a big question.
It basically is the amount. Like at the end of the day, it basically is the amount of deoxygenated hemoglobin. The oxygenated hemoglobin effectively does nothing to the magnetic field.
But isn't the amount the same?
It is, but by virtue of it being this, the oxygenated hemoglobin, if we have, let's say 10 hemoglobins, right? 8 of them are oxygenated, 2 of them are deoxygenated.
Okay, I like that already.
Now we're going to increase the flow by 3 times.
Okay.
So originally we had 8 oxygenated, 2 deoxygenated, right? All of a sudden at this new time point, because we've increased the flow, we're going to have 9 oxygenated and 1 deoxygenated. So it was 8 oxygenated before. It basically had the same amount of hemoglobin, right? That's not changing. It's just the ratio of those 10, or the proportion of those 10, that are going to be deoxygenated.
So there actually is less deoxygenated hemoglobin per unit of volume.
Yes.
Okay, and that's why the magnetic property changes.
Yes.
It's not that we're just adding oxygenated hemoglobin around it.
Exactly.
It's actually because the rate is changing, there actually per unit volume is a smaller amount there. Because that's the magnetic property.
You nailed it.
Okay, that makes sense to me.
Yeah,
okay, cool.
Yeah, the hemoglobin in the blood cells, again, we're talking about a snapshot, right?
Think of it as a tube, right?
Think of it as a tube. Take a little section of that tube. Say we're, again, in a snapshot of time. We're not talking about over time. We're saying take a snapshot of time. You got 10 of these things.
Gotcha.
5 of them are oxygenated, 5 are deoxygenated. All of a sudden, the flow is much more quick. You take a snapshot again. 7 are oxygenated, 3 are deoxygenated.
Because there's less room for the deoxygenated because we're overflowing the brain with oxygenated.
You're giving so much oxygenated hemoglobin per unit of time, the brain just doesn't need it.
And that's because we're holding our breath, which is increasing our carbon dioxide, which is dilating our arteries.
Look at that.
Okay.
All
right.
It's true. I expert there.
Yeah.
Really cool phenomenon.
Yeah.
How the hell was that figured out?
Yeah, how did you arrive?
That wasn't me. So
that's not so. Yeah, well, that's what around
yeah. That wasn't me. So the coming up with the idea that CO2 would alter the blood flow in the brain. This is from like the 1960s.
This is just the blood flow with the oxygenated and deoxygenated. That kind of stems from that.
So that came later, I guess. But yeah, the original how does blood flow change in response to CO2? That was like 1960s, 70s, I think.
Okay.
It may have actually been a little earlier, but like mid 1900s, I want to say, mid to late. This whole idea of deoxygenated and oxygenated was more 1990s, right? 1990s, or maybe late 1990s. The fact that it could be used for MRI imaging, like changes in deoxyhemoglobin. But the fact that it can be used for perfusion imaging specifically, that's sort of the novelty-ish of this paper.
Okay. Cool. And it's like that's essentially going back, the perfusion imaging is a larger, more detailed picture of how blood is flowing in the vessels.
Yeah, exactly. The goal of perfusion imaging is in some organ of interest. In this case, we're interested in the brain. How is blood flowing? How much blood is there?
Is this only would work for the brain?
Yeah.
With the breath holding, is that only really applicable to the brain's perfusion imaging?
It's a really good question. So,
because all of that stuff with the ratio changing, does that apply to the other organs?
Yeah, the ratio stuff would apply. The question is, do other organs have the capacity to respond to CO2? Like, could other organs' blood vessels actually dilate in response to CO2?
Okay.
And I think the answer is yes to some, no to others, and I don't know which are which.
But you're only interested in the brain.
Yeah.
So when you're like picking this topic, is it like assigned to you? How do you arrive at it?
That's a really good question.
Before you jump into that, I'm actually curious on the CO2 dilation.
Yeah.
Would that essentially be like, if someone would say, is that essentially like getting like a head rush, kind of? Like someone getting that from
like cigarettes or something like that. Is that because you're increasing the CO2 in the blood?
Could this person just smoke cigarettes and then go in the MRI and have a similar kind of thing?
That's a good question. So I believe, and I'm not an expert when it comes to cigarettes, but I believe with smoking, you do increase blood flow to the brain.
Isn't that what the phenomenon of a head rush is?
Have an increase of blood flow to the brain?
Yeah. Like when you
I honestly don't know.
Okay, fair.
I don't. I honestly, like, as a researcher, I've had to like learn to say I don't know. because
That's
I
great.
don't like to mislead people. Like, the reality is I don't know. It probably wouldn't be from an increase in CO2. The nice thing is that the blood vessels can respond to other things. So it wouldn't surprise me if, like, the cigarettes had some substance like the nicotine that could actually act on the vessels, for example. I don't know if it would, but I'm sure there are substances that might. Yeah. CO2 is not the only thing that can affect the blood vessels. There are other
The dilation of arteries.
The next experiment for you.
Did you ever like go into the MRI and hold your breath? Were you ever a test subject?
Number one.
Oh, really?
Actually, no. For this, I was number 3. For the first one, I was the first. Yeah.
Yeah. They hooked you up to the high hypoxia machine or whatever it was.
Yeah. So the first one, I was masked up to that thing, and I got the gadolinium too because we had to compare.
Oh, you did already. So but that means you have healthy kidneys, right?
I have healthy kidneys.
Yeah.
Thankfully, thankfully, we're good on the kidney front. Yeah.
So let's go back to just the logistics of this. Like, how do you arrive at this as your paper? They must have had some hunch that this might work. They're not just going to like waste time. Do they assign it to you? Do you pick it?
This is actually a product that I was interested in, like, I want to say 4 years ago. And what happened was my supervisor and I, we went to South Korea to collect data. We did this.
What does that mean, collect data?
So MRIs there are a lot of them around the world. Like the really good scanners, like the high magnetic field strength scanners, are quite rare. They're becoming more common now, but what we call like the 7 Tesla and up scanners, like ultra high.
So how strong they are.
How powerful they are, exactly. Those ones are more rare, and it happens to be the case that there's one in like Suwon, South Korea, which is near Seoul.
Yeah.
And so we went there to collect data because we were interested in playing around with the 7.
There's none in Canada?
There are, but it also happens to be the case that my supervisor has like some level of affiliation with the South Korean Institute.
How expensive are one of these things? Ballpark, do you know?
Really good question. In the millions.
For one of them?
Yeah.
Just to buy?
I think.
Oh, okay. Who makes them? Do you know?
Siemens.
Okay.
Philips. Canon.
Oh, so all the
I
classic
think Philips not.
imaging company, like just like regular camera
Big
companies.
like appliance companies, a lot of them will make it. Yeah. Not all of them. It takes like serious engineering.
Yeah, like I can imagine.
Like one of
it's a completely different department than like making a photo camera for like a trip into Safari or something.
It's like a serious engineering feat, and it took so many years before it came to fruition. And so there aren't too many companies that do it on the like in the big leagues, but there are a few.
Are they generating the magnetic field strength from permanent magnets or electromagnets?
Second.
Oh, electromagnets. Okay,
yeah,
cool.
Yeah.
Okay.
And so basically, you might imagine that the current has to flow through really, really quickly with very little resistance, like almost superconductor level. And in order to get it to that point, the electromagnet is super cooled by liquid helium.
So there's no resistance to the electrons, so that the field change is so drastic.
Basically, like the current that's going through the wire is so unbelievably high that the field then becomes very, very powerful. It's almost impossible to get to that field strength otherwise. So that's the goal, essentially.
So you went to South Korea, you collected data on one of these crazy strong MRI machines.
Right.
And then what?
And so the goal actually was to do something totally different. Our project initially was we were going to use the gas system again, the hypoxia system, but at the 7 Tesla, the higher field strength. And we're going to play around with a few other things and answer a few other questions. The gas system broke on our first day there. And I told my supervisor, I said, I had this idea like 3 years ago. I really wanted to play around with it. I don't know what you thought. And he said, what else can we do? Like, we're kind of screwed now. So let's just see what happens.
Oh, so this was this was just a hunch from you.
It was a hunch. So I had thought about it for a while, and I went in the literature and I was looking around and I saw that we had done it. And I was thinking why, and I could see like decent reasons why, but I was like, let's try it. Like, let's see. And it wasn't so obvious. Like the analysis aspect actually required us to come up with like some very novel sort of steps because otherwise it would have been impossible.
Yeah.
But in general, we were able to make it, for the most part, work out pretty well. There are limitations, but like in general, we were able to push it in there for sure.
Cool.
Awesome.
So
yeah, we're out there. Sure.
You got the experiments, then you had the results. Like, what's the process of, from South Korea to when you come back to Toronto? Are you just analyzing and writing? or do you have to do some like tweaking? Because you don't really have, you can't just like run the experiment at any point. Obviously, you have to go to South Korea.
Right. We collected the data, and that's it. Like once we're gone, we can ask the people there to collect for us, which we did for like one subject. But generally speaking, we're done. Like we have to start analyzing, and if we made mistakes, sucks for us, kind of thing.
Yeah.
Luckily, there were like very, very minor things, and they were like the first few subjects, and so we got away with it. But things worked out, and once we got home, we just started working on the analysis and the processing, and as I said, the writing. Writing came a bit later, but like generally speaking, the analysis was a few months long, and then we started writing.
So, how long from like, okay, you're gonna write your paper on using the machines using the super strong machines with the controlled gas to finishing the paper and having it published? How long was that?
Having it published, I would say,
or like you have to defend it. Is that how it works?
So the PhD you defend, the PhD is like the 3 or 4 papers that you write in your PhD, you compile into one document you defend. This is just like, we sent it to a paper that published it. That process you're saying from collecting the data to publish it?
Yeah. From deciding that this is your PhD to having it appear in a journal.
Oh, I see what you're saying.
Like, not this PhD, deciding that you're going to write a paper on this.
Okay. Deciding that we're going to basically do this. I would say that probably took a year and a bit.
Okay.
The actual collection and analysis was not that long. It took me about 5 months, 6 months to like collect and analyze and do what I had to do. Writing takes a while, and on top of writing, editing, sending it off to journals, getting reviewers to go through it like 3 or 4 times, addressing their comments. They're off for vacation for a month. You got to wait for them.
Yeah.
It ends up adding like a tax on a month here, a month there, and it takes a super long time. So like during that time that you're waiting, you have to do other things. But it takes a while. So the proper amount of time that it should have taken should have been like maybe 3/4 of a year, probably even less. But
expanded out to. And so you're a first PhD. We've had 2 masters of engineering students. So you're saying multiple papers you compile and then you have to defend all of them? Like what's the process?
Yeah. So the first paper was that hypoxia one.
Yeah.
And then there's this, and then we're working on another one, which luckily we basically don't have to collect data for.
Okay.
It's more of a review style paper.
Okay.
So it's like going over the literature and compiling.
Like a meta-analysis kind of?
Not quite meta, like kind of, but more so like we're using our simulations that we developed for like our first paper and like applying it to the literature. So we're like trying to answer different questions.
Oh, cool. Okay.
What did you use for the simulations?
Python.
Cool.
We coded in Python, and there's some really cool like MRI packages that you can use for Python. So it worked out really nice.
There's MRI packages in Python?
Yeah.
Wow.
Yeah.
Do you use COMSOL ever? Or no? Like
COMSOL?
COMSOL multiphysics kind of stuff? No? Okay.
No, but I think I know people who do. I think it's not like uncommon.
Okay.
It's not uncommon.
What does an MRI package in Python even mean? What, you give it the data and it can run like functions and whatever on that data?
Yeah, there are functions and classes and etc. within these MRI packages that are able to handle MRI data. Because MRI data is very specific. Like when you get it, it's
what is it? Is it just, it's pictures, right? It's pixels, so it's just like values?
Yeah, we call them nifty files. And
that's an awesome name.
So many weird names.
I know.
That's an awesome name though, nifty file.
Yeah,
They're 3D though, right?
They're 3D, but they could be 4D. Like for example, they go over time. Exactly.
Okay.
The perfusion ones are like all 4D because we've got a picture every second or every 2 seconds as we're holding our.
You have a 3-dimensional picture with a time component. And
yeah. So each of these files are like a few gigabytes. Maybe 1.5 gigs, like for example.
Big stuff.
Huge, yeah, huge files. So those have to be understood by some sort of package, essentially.
Okay, cool.
And so you don't have to do it in Python. You can do it in other systems too. But
MATLAB has a good one.
MATLAB has. You could do it just on these GUIs that are available from different programs outside of like coding. But yeah.
So it sounds like we're obviously very deep in medicine and human anatomy. Electrical engineering obviously plays a huge role. And now there's a huge computer engineering factor as well.
Mm-hmm.
So you're like all over the place. There's material science, I'm sure, with the what is it?
The gadolinium?
Gadolinium.
Yeah. The big things are definitely the physiology and the computer science-ish, because there's the coding, and the electrical sort of engineering in a sense. Not that there's electrical engineering per se, but there's a lot of signal processing.
Yeah.
And the signal processing is that's like Fourier analysis and
all the fun stuff.
That stuff is very like electrical engineering heavy. Generally speaking, it's sort of a marriage between physiology and physics. Yeah.
Great.
Yeah.
Wow.
That's really cool. What just interested, like, what did you have to do any actual like analytical math or anything like that, or within the code? Like, what did you have to do?
There was some stuff. A lot of the time it's really simple equations, but there are some things like deconvolutions, and I don't know if you know singular value decomposition, like these like more advanced sort of.
I remember hearing that word at some point during my engineering years, but I definitely forget what it means.
Yeah, I won't even get into it.
Yeah,
the
math is a whole other podcast.
Yeah. No, even for me, it's like, do I know what I'm doing when I apply it? Like, I kind of know what it is, but like, I don't have to know so much about what it is. And so like, there are these different mathematical tools. For me, like, I had a background in neuroscience. The last math class I took was like intro calculus in my first year. When I started doing this project, I was like, let me be a little bit in over my head. Things like came to me over time. But there are definitely like a lot of mathy things that will pop up in the simulations. For the analysis, a lot of the time, we have to come up with these different tools. So it comes up.
One question we like to ask is, do you ever have like a big fist pump moment where you're like, oh yes, this finally worked, or the opposite where you're like almost pulling your hair out because you're like, oh, did I completely mess up by picking this?
Mm-hmm. You're saying like that?
Like, well, because you obviously had severe influence on the trajectory when you switched to breath holding, which was a feeling you had. So like, was there ever a point where like, what am I doing? And there's another point where you just gave a big fist bump? Because...
Yeah, the hair pulling was like definitely when that machine broke, and we're in South Korea, and I'm like, I'm so far from home, and I have no idea what I'm going to do here for 2 weeks.
Yeah,
that was definitely a hair pull moment, and I think like within a day, I spent like the entire day with my supervisor, like going back and forth, really studying it out, and like going through these ideas. And eventually we arrived at this, and that was, I would say, the fist bump moment. And like throughout like the analysis, there are all of these hair pulling moments. The code's not working, that this isn't working, and the analysis isn't working the way we really expected. And then a lot of the other fist bump moments were like, oh, like we sort of thought about it from a very different like light bulb moment, lens, and all of a sudden it's working. And so this happens all the time. Troubleshooting is like the number one thing that happens in a PhD. This is like your day-to-day, except for when you're writing.
Yeah, okay, troubleshooting.
Troubleshooting is super common. So there's a lot of hair pulling, but it's like small hair pulling. Like, you know it's going to work out in the end. It just sucks for the moment because you're like, how am I going to figure it out? Even though I know I'm going to figure it out.
Okay, cool.
Mm-hmm.
Yeah, because we spoke with some people who are like, at one point I thought that I'd wasted a year of research and this is just not going to work at all.
Yeah, that can happen too.
Yeah.
I worked on a project. It was supposed to be my third project. We collected the data in South Korea too. It was another one of these like, let's just try this. And it didn't work the way we like thought it would.
Yeah.
And it wasn't necessarily wasted data, but it was a lot of time that we had put into like the analysis.
Panning out.
Yeah, exactly. And that happens sometimes. I think one of the most important things in research is to be honest. Like, it's science at the end of the day. Science is about being honest. It's about
you can't cook the books, right?
Exactly. Like you're looking for the truth, and if things don't work out, it sucks for you, but you don't want to mess it up for everybody else who's going to end up using it and saying, well, wait a second, does this really work? So you have to try to be really honest, and it's hard at times, but...
And you have your professor or your supervisor to keep you honest. And you spend a lot of time with this person, right? Your supervisor?
Yeah, I'd say like we probably meet once or twice a week. When we were in South Korea, we were meeting every day. We had dinners together. Like
you got to know him.
We got to know him for sure. But yeah, we spent time together. We've been to Italy together. We've been to England together. We've
gone all over the world together.
We were supposed to be in Singapore together a few days ago, but I decided I didn't want to go on a long flight to Singapore.
Yeah.
But otherwise, like we've traveled to three different continents together.
Wow.
Is your wife jealous?
She joined sometimes.
So it's like, you remember all these nice vacations without me.
She came to South Korea. She's like, I'm not missing an opportunity to do that. She came to Italy.
Beautiful.
It's been a good excuse to travel. For sure.
Yeah, I'm sure.
Yeah.
So you're writing this last paper right now and then wrapping up the PhD?
That's the plan, yeah. So the last paper, in a sense, kind of helps me write the PhD, like the thesis in general, because it's so general and it's so like literature review heavy that I have to anyway like do all these things when I'm writing the thesis. So I'm kind of doing both at the same time.
Okay, cool.
Yeah.
And so is the thesis as long, or is it like a consolidated, more concise version?
So the general idea is, let's say you write 3 papers, put those in a cohesive text, create an intro that like sort of sets up for all those 3 projects, and a conclusion that kind of just.
So it's not that much work compared to the actual academic.
No, not even close.
Okay, interesting.
Once you have, it's not like a humanities PhD, which is I think a little different because you don't necessarily publish along the way. Some people do. Your thesis is kind of like the final thing you put out, and it's all building up to that. Whereas for science, it's like you've already done your 3 papers or whatever it is, so just put them in the document and put an intro.
And then just be prepared, and then you defend it. What do they do? Is it like they attack?
They attack a bit.
Yeah,
I've done dissertation, right? Or
yeah. So you present it. You present basically like a 30-minute project or a 45-minute presentation of the projects, and they'll watch along with like the whole school, whoever wants to come. And then afterwards, there's like a 2-hour session where you sit there and they go around in a circle grilling you for 2 hours. Literally 2 hours.
That's how it works.
So they don't like grill you saying like, oh, how could you have done this? It's more like, why did you do this? Like, how do you know this would have worked? How do you know this was like the most rigorous approach? Sometimes the answer is it wasn't, but like they kind of like go around and like want to make sure that you were doing things properly.
Is that their like full-time job, or do they do other things?
They do other things. So no, these are mostly researchers. It's like my supervisor, for example, would be on the board for somebody else.
But he can't be on your board.
He kind of is. He's technically one of them, but I don't think his vote really matters that much. Effectively. Like,
and they vote. So then they vote to like, do you get your PhD or not?
Exactly.
Have you been going through your breath holding reasonings like a lot?
What is that? What is that?
Helps, by the way. Like time, for sure.
Yeah. That's how we do. We can start selling this as a service.
Yeah.
But when is that? When are you expected to have that? Like, I don't know, court hearing, whatever you want to call it.
So my supervisor and I discussed, and we're hoping to do September, like late September, like last day. Originally the plan was like a little bit later, but I think we're going to try for then. And so that means there's going to be a bit of a push. I'm going away for a month now.
Very nice.
And so when I get back, I'm going to have to like really put in a bunch of work to get the thesis done. But it'll be a lot of like preparing the presentation, going over every project I've done, everything.
In depth, like you got to really be ready.
In depth, yeah, for sure.
Because they're doing that.
The reality is like they're never going to ask, they shouldn't, unless they're really, really good. They probably won't ask you a question that gets you super, super, super off guard.
Yeah.
Because they don't, like, it's almost impossible for them to know your research better than you. But they know the general field better than you. So they might ask you things that are maybe a little more,
over here.
Yeah.
Interesting.
And have to be able to answer that. So, yeah. But they will want you to know for the purposes of, like, how did you do this thing? And if you can't properly answer it, they might say, They won't fail you for it, likely, but...
Okay.
Yeah.
Well, good to know.
Yeah.
Well, I think that wraps up the session. Has anything else you want to ask, Aaron?
I think I'm good. I think that was amazing.
That was amazing. Jacob, thank you so much.
It was a pleasure.
Thank you.
Next time I get an MRI, I'm holding my breath for the entire time. No, but really, thanks for coming. And we wish you all the best in your PhD endeavors.
Thank you guys so much.
Awesome.
Fun.